Hello, we're back. I did the last stream a few hours ago, and that was just a little Desmos primer, showing you how to graph some shapes, showing you how to do some other stuff. So, what we're going to do now is go straight back to that physics solver thing, that physics impulse solver. Let me just make sure the stream is up and running, that I can hear myself. Yep, I can hear it all. Okay, cool. So, where we left off, we had shape drawing and circle line stuff. So I showed you all that. I was vague in a few spots, but I'm sure you can figure it out. I have the link in the description of this video. Yeah. So, I can give you the link right here. Share a snapshot. I will paste it right here. There you go. Here you go. Here is the link. In case you can't find it anywhere else, to a little snapshot of the thing we did last time. If you don't know anything about Desmos, then you should probably start here and look at that live stream that I have linked in this description. Anyway, let's just get right into it. So, we're going to look at the engine. Let's take a snapshot of some point in time. Once the capsule's flopped over like that, let's drag it and drop it on top of the circle like that. That should not happen. We do not want something like that to happen. Okay. So you see, if I zoom in, I love this zooming feature. We'll zoom in all the way. And you see that we have some transparent shapes drawing too. We have a transparent capsule. These are the positions at the start of the frame, and the solid ones are the positions at the end. So I'll just disable those final positions, and we'll look at this contact right here. This will tell us everything we need to know. I should probably fix this really zoomed in text, but we'll worry about that later. Okay. I guess I could just take a snapshot of this. It doesn't really matter. Oh man, I'm trying too much stuff. I need to organize this. No matter. Okay. Yeah, I probably should clean up all this stuff. It's kind of hard to see the text, isn't it? Well, we don't need everything. We'll just take a little snapshot. Oh my god. Okay. Okay, that should be good now. Zoom in. Yeah. It's a capsule circle collision. Penetration. See the point. We have the start velocities. Start velocity. We have the positions open. We'll probably need that too. It's going to take a while just figuring out the exact information that we need. My mouse is glitchy. Okay. Is this because of my mouse or... Yeah. Yeah, so when I drag stuff with my mouse, there's some kind of mechanical issue. Oh no, this is just some interaction between trying to drag the entity and drag the UI window. Whatever, I'm not going to worry about that. Okay, let's just start over. And let's start commenting out a bunch of stuff that we don't want to draw anymore. Where should we start? All the way down here. Let's comment out all this stuff. Just wrap it in a compilation thing. Okay. Do that to this stuff too. I have the scaling thing. Scale frame buffer right there. I'm going to draw that text telling me the position of the mouse after I already scale everything. Which is right here. And we got to start cleaning this up. Once everything starts working, of course. See how it works now. Oh, I need to get rid of that grid. Okay. Just disable this too. Okay. Beautiful. Cool. Okay. Okay, so those final positions should not be like that. They should not be getting sucked into each other and then flying apart like that. That's not right. And we're chugging right now because we're zoomed in. There's a lot of... We're not doing multi-threading or SIMD stuff. We're just... we're drawing all this text, all these UI windows, all these shapes, all these little circles, and then we're zooming in, like, just blitting to another frame buffer, then copying it back. So it's very expensive, but we don't need to worry about performance right now. We're only worried about fixing the impulse solver. Just want to set it up so the slider's positioned all right. Yeah. Okay. So this is where the contact first happens. Let's make sure we have everything positioned nicely. Oh man, there's just so much information. It's going to take a while just to make sense of this. Yeah, so this is just going to be a stream where you watch me debug stuff. It's not going to be talking that much. I'm trying to figure out my own stuff. If you have no idea what I'm doing, I think I've already gone over this. But there's a little Desmos example and stream that I did earlier that you can look at. And then once you're familiar with that, if you want to see the process for how I debug this stuff, then you can look at this. But right now I'm debugging a capsule versus a circle. And the whole problem is that I calculate, there's some kind of sign error where I calculate the relative velocity between the shapes incorrectly. And then I apply that to the velocities of the shapes incorrectly. And that leads to them getting sucked into each other and exploding apart. Where instead we would just want them to smoothly slide off each other like would happen in real life. We're making a physics engine. This is not physically realistic, what's happening here. I'm gonna take a little snapshot. Push it up over here. Let's just minimize. Whoa. Minimize that. Okay. So let's look at the positions. The start position of entity A and B. This is ridiculous. Yeah, so when I first got the impulse solver set up, I had copied over the Box2D Lite library to my own format. And then I plugged in my shapes and I started stepping through it. And of course everything was wrong. And so I had to plug it all into Desmos and verify each step. And over time that took many hours. But I was only doing a little bit per day. I wasn't grinding on it like I am now, so it took like 2 weeks. So we're going to see yet another slow, laborious process where I'm just debugging all this stuff. And eventually, we'll fix it. But it's going to take a while. But if you want to know the code that I'm starting with, or the code that I'm replicating, I'll just show you a link. It's called Box2D Lite. It's by the legendary Aaron Cotto. I don't know how to pronounce his name. Box2D Lite right here. And you can download the code and then look through it on your own. And start learning how to write your own impulse solver. Loud penetration, bias factor, get that plugged in. Restitution is how bouncy it is. Like if it's 0, then they're just going to stick to each other. If it's 1, then they're going to bounce apart with their velocities are just going to be reversed completely. So this was a different snapshot that I took. Let's get their new angles. Each other where? It's weird. Okay. Start angle is 0.1. Starting angle is 1.6. Okay. 1.644297. We're going to look at every single piece of data and plug it in. It's going to be very slow. I'm just demonstrating that this is just one of the things that you're going to have to do if you want to get comfortable writing physics. Oh, jeez. And typos. Six 44297. Starting position. $12.990892. Yeah, that looks right. It's the circle position. .008,563. Yeah. 98943. Yeah. And then the collision point. I think that's over here. 13.935. 27. 1.996, 244. Okay. And so these are the lever arms, R1 and R2. Those are the angles from the contact point to the center of the shape. And the R1 in this case is, let's just make sure they match up. What we're reading out in the solver. R1 is negative 0.073. That is not what we have here. We're already getting discrepancies. Did I plug in the wrong value? Yeah, I did. Nine three five 127. Okay. So as soon as we plug in all the starting information, we're going to set up a scaffolding in Desmos that will recreate all of these calculations and hopefully lead us to the correct value that we can then compare against the incorrect value of the engine. That's essentially what we're doing. We're printing out all the starting information for the contact, and then we can see the incorrect data in the relative velocity, rel-val right here, negative 5x, 35y, that definitely can't be right. We're going to calculate our own relative velocity in Desmos and compare against the engine and figure out exactly where it goes wrong. That's what we're building up to, and it's going to take a long time for anyone who doesn't know what's going on. Long, long time. So anyway, R1 is the lever arm between the contact point and the circle. I could probably draw them for you. Let's draw a line there. With our handy little F draw line function, we'll draw a line from R1 to the center of the circle, right? Why? Defined R1 in more than one place. Okay. Where have we defined more than one R1? Down here. Let's get rid of those. I copied over a lot of stuff from another solver earlier. Okay. Where is that line? I want to see that line show up. Oh. Okay. Let's see. Probably need like circle plus R1. Yeah. Okay, there you go. That blue line is kind of like a representation of the vector from the center of the shape to the contact point. We'll do the same for the capsule. There we do cap 1. Yeah, there you go. Cool. And just to verify that those numbers are correct, R1 negative for X, it's negative 0.073435. 435, yep. And then Y is 0.997301. Yeah, it's close enough. And then R2 9442235 negative 0.82335. Okay, perfect. At least the lever arms are correct. And then the capsule velocity, this is going to be different. This is an old variable that I had from a few days ago when I was working with this. You can see for rigid body A, that's the circle, the starting velocity is 0. That's nice. Yeah, that's correct. And then the capsule velocity, you know, this is going to be different because it depends on like how far I drop it, where I drop it from when I drag that capsule. And that is going to be, start velocity V is, because it bounced off the wall, it has a little bit of an X component to it. It's negative 0.030024. And the Y component is negative 6.811701. Circle velocity is 0, the bias factor is 2, the allowed penetration is 1. Restitution, I'm just going to make them perfectly bouncy. The bias factor. What's wrong here? Separation. Okay. I think I have that. Separation. What is separation again? Separation is something important. It's should be negative, right? I don't know, whatever. It has to do with the penetration. I think it matches up with the penetration. Yeah, so you look at the penetration, it's 0.109533. That's how deeply the objects are penetrating. The separation, I feel like that should be the negative of penetration, but I guess we'll figure it out as we go further. So we'll just make that variable separation. Separation is 0.1095. Okay. And that's the bias. That's how much we want to correct. Just look in the code to see what the separation is exactly. Separation. How do we determine the separation? This is in circle versus line. Capsule versus circle, static resolution. Outer capsule point minus outer circle point. I feel like that should be the other way around. I feel like it should just be the negative of the penetration, right? Let's make a little note here. Again, everything is confusing. I have no clue what I'm doing, so I'm not going to make any massive changes right now. We're just going to try and piece together where it could be going wrong. I should store those too in the contact, like where the points are between them and then subtracting them. It's like the etymology. Yeah, the penetration is positive. You're like seeing how much they're penetrating, but separation that should tell you how far apart they are, right? And if they're like touching each other, then the separation should be negative. I suppose you just make it negative, and let's see if that influences the bias. Okay, yeah, so you can see that the bias is definitely pointing in the other direction because we take the minimum between 0 separation plus allowed penetration. Is that right? I have no idea. Let's just keep it positive for now. Contact normal. I think CN stands for contact normal, and of course we don't have that. And we should see what it is. This printout right here. Mass normal. Do I ever print out the... Okay, yeah, the normal's right here. Just add that real quick. Right here, let's do CN for contact normal equals... And we see the normal right here. Can't draw. Yeah, there we go. 0.073434, comma, negative 0.997300. If I want to draw that, just draw a line, draw a line, and we'll make it come from the point to the point plus the contact normal. Like that. I think it overlaps about one. Yeah, it's the same thing as one. Yeah. Okay. So this blue line, that is the normal. It is pushing the circle down, or rather the capsule out. I guess it just depends on how we interpret it. But it's the exact same as the lever arm between the circle and the contact point. Penetration. I'll just hard code that to separation. PN. That's something to do with the penetration normal, the impulse normal. I think that's the impulse normal. That's something to do with down here. Go to, I had it set up in the circle versus line. I just want to remember what PPN is. Mass normal times the relative velocity plus the bias. Let's copy that into this thing. Oh, I already have it. It's just all mixed up all over the place. So, do we have the mass normal yet? Down here is the mass normal, and that depends on the mass normal components. We call this J component. I guess J here is for the impulse. Cap J comp, whatever. Oh, and the inertia. Okay. Gotta figure out the inertia of the objects, and I think I really hope I print them out here. I don't think I'm printing them out. That is unfortunate. I guess I can just step into the code. I need to do it. Right here. Okay. Generate snapshot contacts. We're just regenerating the contact for that snapshot every single frame. We're not storing them or doing we're not warm starting or doing anything fancy yet. We're just trying to make sure the geometry is correct. So we're just regenerating contacts every frame. So this is where I take the entities, see where they start. This is the circle entity. Well, that doesn't really matter, because this can all change based on where we are when we actually sort through the contacts. So we'll go here. Is this even gonna run? Oh, when I added that, oh god, when I added those comments, I shifted everything down. Yeah, okay, whatever. This is a circle versus line contact. Let's get that. Circle versus line. Capsule versus circle. Okay, perfect. So the rigid bodies, this is the capsule. Okay, and the inertia, or the inverse inertia for it is 0.355. That's what we're going to plug into the solver right here. Yeah, so we'll call this cap inverse inertia, cap inverse I, or the inverse inertia. We'll define it up here. Cap inv I equals this value. Okay. We'll do that. Let's call it circ. Circ inv I. That's rigid body A. You can see the type is a circle. Inverse I is 2. The moment of inertia is smaller for the circle because it's not stretched out as much. The capsules is way larger. I mean, the moment of inertia depends on how... I could do a demonstration if I had a little spinny chair, but it just depends on how much of your mass is distributed outward away from your center of mass. You can look it up on Wikipedia or whatever. But anyway, the inverse inertia for the circle is that. Okay. That looks realistic enough. Mass normal. Circ inverse mass. Plug that in. As well as the cap inverse mass. Let's copy those over. Need to make a note to just make a bunch of notes to myself. I love Obsidian. Okay, make a note of that. Man, I forgot. Oh yeah, print out all the stuff. Okay. Just showing you the process. Like I move it over into this other window. Just to get it out of the way. I only have one monitor I can share with you. Call this the capsule inverse mass. Cap inch mass. That'll be some value. That'll be some value. Inverse mass of the capsule is 0.5. And the inverse mass of the circle is 1. Right? RV circle, 1. Yeah, okay. That'll be 1, that'll be 0.5. Okay, so we should be getting closer to the mass normal. Oh yeah, just need to change my names. We'll call this circ jconf, cap jconf. This is exactly what you see happening in the code for box 2D. So that's the mass normal. That's 0.563053. Let's see if that's the same in our debugger. So you see the mass normal here, 0.563054. And that is basically what we have here. Just a little bit off, but that's fine. It's like the 6th decimal place that there's a difference, so that doesn't matter too much. So then we multiply the mass normal times the old relative velocity plus the bias. And I don't think we have that defined. Look at this other thing. Where do I define the old relative velocity? It's the velocity of the circle minus the velocity of the line. Okay, yeah, I just call it old because we're going to calculate a new one after we apply the impulses. That's fine. Just make this dark too. There we go. Much better. We have the capsule velocity, the circle velocity. We have Cn. Drag that up here. Again, this is the contact normal, collision normal. And so this is where we have the first problem, because in my code, I had to flip around the signs when I was first getting into work for the circle versus the line. And that was just for a static versus a dynamic body. The static body being the line. That's just static geometry. It doesn't move. That's just how I set it up in my engine. The lines are static versus the dynamic circles that can move around and adjust their positions and velocities. And based on that, I had to swap around the signs. And I think that is still leading to incorrect directions and applied velocities and impulses when the bodies are dynamic. And that's also depending on the order in which I store the rigid bodies for the contact. Like, I have rigid body A and B, And those references could be swapped depending on how I input the bodies to the circle versus capsule collision detection and solver. So there's a lot of moving pieces we need to split apart and figure out where it's going wrong. And then relate it back to the only functional correct resolution that I have, which is circle versus static line. And somehow get all those signs to line up correctly. If that makes any sense. I doubt it does. Don't worry. If you want to understand, you just got to do this on your own. I can't help you. You have to help yourself. So this is V. That's the relative velocity. I just call it dV. Is this correct? Contact normal. So to get the relative velocity, or the normal velocity, we take the relative velocities, which is the starting velocity minus the cross product of the lever arm and the angular velocity. Oh boy, okay. So there's a few more components we need to piece together. And oh, we're just at that collision, so we can step into it and see. And that looks like that is correct. Negative 0.03, negative 6.8. Let's just see if that's what we have. Negative 0.3, negative 6.8, yes. And then the A velocity is going to be 0, 0, or basically 0, 0, you know, like 5 e to the negative 10, that's basically 0. And then the lever arms, 0.944, negative 0.823. Yeah. And then A is going to be negative 0.07, 0.997. Yes. Okay. Then the angular velocity, that's basically going to be 0. We'll just plug in angular, circle angular velocity is 0. And I think the capsule is spinning very slowly. Point. Let's plug this in. We're getting there. Getting close to figuring out what the correct velocity should be, and that's the hardest part. Or the most tedious part. Well, I guess the hardest part after this is figuring out the signs. Whatever. So, let's just call these linear, like cap, lin bell, and circ lin bell for linear, because now we're also going to have angular velocities. Cap, ang, bell. And that's going to be that value. Because it's two-dimensional, you can only rotate around the axis pointing into the screen, and that's just going to be a single one-dimensional scalar value. You don't have 2 dimensions for linear velocity, which is giving you the x and the change in x and y. When you have angular velocity in 2 dimensions, it's just a single scalar value. If it were 3D, then you would have to determine the axis in 3D space, and then you would have a scalar value at which you're rotating around it. But in 2D, we can ignore that whole vector because it's always pointing into the screen, I don't think you need a whole tutorial on that. And then the circle, angular velocity is 0. We're going to do this exact math where we're going to take the cross product. And I had these set up based on a bunch of other stuff, but it's going to be a mess. I guess I could step into it. But this is a floating point crossed with a vector, which is this. And I can make a function for that in Desmos if I don't have one already. A10, perpendicular, CCW. There's a lot more functions that I didn't show you how to make. But I'm pretty sure if you understand how to make a function in Desmos, you can understand how to transfer the C code to one. I think I have one. Vec2 cross. Yes. Let's see what it's called. Vec2 cross R1 penetration normal. That's the angular impulse. And I'm burning out. It's hard to stay focused. Whatever, we'll just get through this part. Vec2 cross. What do I call this? Scalar. I'll just call it scale Vec2 cross. Because the first is a scalar, the second one is a vector. We'll do negative s cross vector.y. I'm just copying over the code that you see. It's going to be a vector. It's going to be a two-dimensional value. Negative s dot v dot y. Negative s dot vy. And it's going to be s dot vx. Okay. Call this the calculation down here, or rather where we calculate the relative velocity. That's the critical part. That's what I want to figure out, what the relative velocity is. So it's going to be the capsule velocity, the capsule linear velocity, minus the cross of the angular velocity with the lever arm. We'll just call it cap though. Cap lin bell, because we have that negative sign. This isn't, I guess the first step is I just want to see if we can get a similar result to the engine. It's going to be wrong. I'm saying that it should match the engine even though the values are definitely wrong. And then we can see where in our calculations we need to adjust it to get the correct result. And at that point it should stop matching what we have in the engine, if that makes remotely any sense. So we have the negative linear velocity of the capsule minus the cross product between the cap angular velocity with the lever arm. Yes. And what that's telling us is that at this point, at the point of the contact, you know, these shapes are composed of an infinite set of points around the boundary of the shapes. For that specific point, we're determining how much it's moving based on the angular velocity, because, you know, depending on how the shape rotates, this point is going to move relative to the other point. I don't know if I can explain it that well. I have my windows open. It's getting kind of chilly, even though I'm on the treadmill. And so the cap velocity the y is positive, so that probably isn't right. That's probably a clue. But anyway, let's add that to, let's just do the same thing for the circle velocity. I think we have all that. Circvel equals the circle linear velocity, that is positive, plus R1 crossed with the circle angular velocity. So we do catvel minus circvel, which is negative 6.96. Let's see if that's correct. With the normal. Negative 6.96. Okay, that's exactly what we have in the engine. That's good. Even though it's wrong, that's good. We're matching up with the engine. We're correctly modeling the internal state of the engine in Desmos. That's a step in the right direction. And you can see if we also print out dV, thought we would be. Is this just telling us the final relative velocity? Whatever, let's calculate the impulse normal next, which is, let's see if we get that right. It's the mass normal times the velocity normal plus the bias. The bias is 0, which matches up what we have in the engine, which matches up with what we have in Desmos, I mean. Pn is 3.77. Yes. Okay. And Pn with the normal, pushing them out from each other, is x.27, y negative 3.7. Yes. And then we plug that all into the impulse calculation. Oh, this is like a break point to determine, because they explode, I'm just checking if the velocity exceeds the value of 30. In this case it will, and so it won't. Yeah. Okay, well, anyway, we're pushing the circle down. That's not what we want to do. What we just did is we took that impulse times the inverse mass. Pn is normal. How do we calculate that? dPn is J in Desmos. Man, I'm just saying all these words, and there's no way you're going to be able to follow what I'm saying. I'm sorry. Oh, we're not worrying about restitution here. Interesting. Yeah. Okay. We're not worrying about bouncing them off of each other. So we're just treating restitution if it's 0. As if it's 0, in which case, what we do instead is we have the relative velocity plus the bias, which is 0 times the mass normal, and that is J. Should probably label all these correctly. Like, I'm just using the original box 2D light variable names, and of course, I don't understand the thought process behind calling it DPN. I think it has something versus DPT. That's the tangent, so I think the N in DPN is normal. Delta impulse normal? I don't know. So anyway, let's just crank down restitution to 0. For this one. Wherever restitution is, yeah. Let's just constrain it between 0 and 1. Okay, so restitution is 0. And this is just the mass normal. E relative velocity, V rel old. 6, negative 6.69. Oh, and then this is the impulse, because we multiply it by the contact normal, and that's the next step. Mass normal is correct. EPN is correct. PN is not correct. Why is PN not correct? 0.37 times the normal. Contact normal. 0.073. Yep. Missing something. Oh. No, I'm not missing anything. Okay, this is just wrong. Let's just ignore J and J for now. What we actually want is DPN, that's correct, then the resolution normal. That's what we're multiplying by the inverse mass of, let's just call it circ nu vel. We're doing the circ inverse mass times Pn, yes. Let's do the same for the capsule, new velocity. Cap nu vel equals or subtracting it, like negative. F val. Sorry, I don't understand this. I do not understand. That new velocity definitely is not right. I'm living directly north of the regional airport in Seattle, so with the windows open, you can hear the planes coming by all the time. I wonder if the microphone's picking it up. I don't know. It's getting dark in here. Just one last step. I just want to figure out if I can get this print out exactly the same in Desmos. But for some reason, it doesn't understand it. Isn't that weird? Why don't you understand it? Cap Nouvelle. Man, I went one step too far in the debugger. I guess I could store a temporary variable value there. 0.5 times PN. Somehow the velocity of the capsule flipped. Now it's going up. Velocity, where's velocity? Right there. We do a lot more iterations over this, so eventually, I don't know how we end up with a relative velocity like that. The starting velocity for B is 6.8, and then the sign gets flipped, and then the velocity, okay, the first iteration for the velocity is, after we do the first iteration, is negative 0.33, 8.8. Which doesn't look exactly correct. Oh, that's because we still need to add the tangent velocity. But I'm still incredibly concerned with oh. The impulse. I said oh, but I'm still wrong. This is tricky. print it out down there. Just set up the debugger. No operator star matches operators. That's amazing. Let's do dot X dot Y. Please. Yes. Is it some operator issue? Some overloaded operator issue? I don't know why this is happening. I don't know why the sign of velocity is flipped. This could be a deeper bug than I was expecting for just a sign issue, because the velocity was clearly negative y and now somehow it's positive y. And that makes no sense to me. So it could be an operator issue. Vec2 operator minus equals. Do this manually, compare them. Well, I just shut it down, so we would need to put in new positions now for the shapes. Which means we need to put in new positions and new velocities. But I think everything else should be the same. It's not that much work. I guess the only way to speed up the iteration time on this would be to detect which text I'm mousing over in the UI system, add a little system to double click it to highlight that, and then copy and paste it into my clipboard on the computer. I would need to go through some Windows calls for that. I haven't set anything up like that yet for text highlighting or copying or pasting. I could, and that would only take like a day or two. And I guess it would be worth it if I just want to directly copy and paste values from the engine to Desmos. I can worry about that later. What I want to figure out right now is to test for any discrepancy. So what we're going to do is back to B val temp is B velocity. Back to new B val equals B val temp minus E inverse mass times PM. Let's see if that compiles. And we're just gonna assert velocity dot x equals new b val dot x, and same for y. It will crash as soon as those aren't right. Well, that's not helpful at all. Oh well, at least we had a snapshot of what it was before. Yeah. Whatever. I think that is where I want to move to. Yeah, that is where I want to move to. Okay. Oops. Get back to that snapshot of capsule versus the circle. This one should be it. Yeah, capsule circle. Temporary velocity should be going down. Not doing something right. Start velocity B, e to 4.55. So why does it say that it's positive 4.55? Why is it doing that? There's some mismatch between what I'm printing in the debugger, and I don't know what's going on. This is weird. Because that's the capsule. And it's definitely falling on that frame. Did we save what the beginning velocity was in the snapshot? Start velocity, yeah, so we can see the starting velocity right here is clearly negative 4.55. Starting velocity, yeah, we store it right there. What the hell? Where could that change? Doing something really weird. Maybe there's a memory issue. I don't know what could be happening, because here's what I'm going to do. We store it up here. I'm going to assert that it's the same value down here. If iteration equals 0, we're going to assert that velocity.x equals cs start lb.x. Same thing right there. Oh, oops. Okay. Yeah, I'm getting really tired. It's just the last thing I want to test. What the hell? Huh, that's weird. It's very strange. There's more stuff I need to figure out when I'm dragging them around. Like, I'll draft. Huh. Okay. That's so weird. I'm doing something really weird. Okay. Well, I can't focus anymore. I don't know what that problem is. God, that's horrible. Just gonna try one more time. Okay. Inspecting the state. That doesn't happen when I'm just solving the impulses, but I trigger the assertion when I go to inspect the state. Or, oh no, that's only okay. This is just a different routine. That's good. That's what we wanted to happen. I just want to see if it's the same in the regular solver, because this is like a separate function on the side that recalculates all the contacts when we're taking snapshots. But for the actual full impulse solver over here, we're going to do the same thing. Take the same thing here. Iteration equals 0. We'll just have something called like vec2 start b start velocity. And we'll just set it to null. And then if it's the first iteration, gonna do equals the b velocity, right? And then down here, I'm going to check that it's still the same. Okay. Okay. That's great. So we can see that the starting velocity is negative 1.66, and then the velocity once we get down here is positive 1.66 or positive 0.166. So we're somehow in between here and down here. We're messing up that velocity. I'll just drop this in everywhere to see where it could possibly, like where the earliest possible instance of it going wrong could be. I'm just going to litter the code with all this stuff, and then we'll see where it happens earliest. Okay, so we're catching it a bit earlier. Some weird sound outside. Okay. This is great. This is exactly... I mean, this sucks, but at least we're getting closer. Okay, so what happens right after we do dv, and we set it equal to negative velocity. I think this might have something to do with me stacking the operators, where I'm accessing the memory of the velocity. Like, let's just store it in a... Let's just do, like, vec2 temp bvel. Just b velocity, right? This is a new instance in the memory, and we're just going to plug that in instead. I think this has something to do with me doing my operator overloads wrong. Okay. Oh, dude! That's totally different from what was happening before. It immediately falls over. Dude! That's crazy. We got it. Okay, so it is an operator. That's crazy, dude. Oh my god. That's wild. Bro. Dude, this is amazing. Okay, so there's some operator issue. I'm too toasted to figure it out right now, but man, that's crazy. Oh my god. Well, of course, like, they don't push each other out correctly, but at least they're not exploding anymore. Dude, that's so cool. Nice. So nice, dude. Oh my god. Yeah, so when I push them into each other, there's that's probably another bug where I'm not calculating the bias correctly, and I know it's like a similar issue for when I tuck the capsule into the wall. Yeah, it's not pushing itself out from that. But at least we solved the immediate issue of these exploding. That's beautiful. Okay, and that definitely is, because when I do negative B velocity, when I was doing this, was somehow adjusting the memory, and I think that is because of the operator overloads over here. So I do operator minus or minus equals. I think it's because I'm taking the reference to it. Yeah. I'm taking a reference to it. And I'm somehow returning the value where I just swapped them. I don't know, I'm going to need to thoroughly debug this. But I think it has something to do with the operator thing I do here. So I'll figure that out. I'll post a little video showing off the progress and give a little warning about how you handle your operator overloads. But that'll come in a day or two once I thoroughly understand the problem. But I am just so absolutely stoked that it's actually working. I just want to... Okay. Yeah, that is weird. I drag the capsule out of the way, but the circle still thinks that it's intersecting it. Huh. That's crazy. And I'll drop the capsule onto the circle and nothing happens. That's another thing I need to figure out. But the immediate issue of the capsule exploding when it collides with the circle, that's been fixed. Because once again, the operator overloads. So we got a little bit closer. Thank God. The stream wasn't a total disaster. It just took... How long have we been going? It just took almost 1.5 hours to find. So that's amazing. So I don't really know how to end it. There's still a lot of problems. But at least we got the explosion fixed. So yeah, thanks for... I don't think anyone will ever watch this. It's just a document for myself, so that's awesome. All right, I gotta eat dinner. I'm exhausted, but thanks for tuning in.